Okay, so review question 3. Got a question states, so an ideal fluid flows at the rate of 0.2 liters per second through a horizontal pipe of 16 millimeter diameter. The pipe then narrows to a diameter of 4 millimeters. What is the pressure difference between a point in the wide pipe, to a point in the narrow pipe? Okay, so it's an ideal fluid flow question, so that's our note of the first sentence. So this is, to solve this problem, we're going to have to think of Bernoulli's equation. So again, I'll start with a sketch here. So let's see. Try to draw this reasonably accurately. So it's exactly, it's going to 1/4 of the diameter. So it's a large narrowing. And draw this somewhat accurately. Okay, so it's going to a narrowing up here. It goes to 1/4 of its diameter. Okay, and then we're looking at alright, so what do we have here? We know that this diameter is 16 millimeters, and then this one is only 4 millimeters, and then we're looking for the pressure difference between a point in the wide and then a point in the narrow. Alright, so we can write Bernoulli's equation that states that the pressure plus the potential energy term plus the kinetic energy term per unit volume is a constant. So let's start there. So stating that P1 plus rho g y1, so that's the potential energy per unit volume term, plus the kinetic energy per unit volume, 1/2 rho v1 squared is equal to P2 plus rho g y2 plus 1/2 rho v2 squared. So actually I need to update the question, so to save myself to repeating this, I'll add into the slides here that this ideal fluid, assume rho of the fluid is water. It's the same density as water, so I didn't want to put water in there in case you think that the water has a viscosity, so I'm going to pick an ideal fluid that happens to have the same density as water. Okay, because I know I need this rho term. Okay, so what's useful in this question, it's a horizontal situation, so we don't have to worry about changes in the height of the water flow, so I can remove these two terms since y1 equals y2, so they're at the same horizontal level. So really just looking at the differences in the pressure will be due to differences in the speed. We expect the pressure at 2 to be a smaller value since the speed is higher due to continuity. So if we're looking for the pressure, I'm looking for a positive value, I'm going to do P1 minus P2. So I know the pressure where the fluid is moving slower for an ideal fluid, the pressure there is higher. So P1 minus P2 will be 1/2 rho V2 squared minus V1 squared. So I hope I haven't skipped too much steps there, but if I bring this 1/2 rho V1 squared term across here, the 1/2 rho is common to both of those terms, so I can take that out and think about the differences then in the squares of the speeds. And to get we again updating the question, assume that we have the density, I need to think about the speeds. I know the no, I don't know the speeds in either place, but I do know the flow rate, and the flow rate's linked to the speed of the area. Okay, so let's work on that part of the problem. So I know that, let's switch colors here. So I know that Q is equal to V times A, or A times V. So if I want to think about the V1, for instance, I can think of then the V1 is Q divided by A1. Now the Q is not in the correct SI unit term. It's in liters per second. Now a liter is 1/1000th of a cubic meter. So this is going to be 0.2 by 10 to the minus 3 meters cubed per second. We don't have to change anything with the time, it's per second. But 0.2 liters, again, divide the amount of liters by 1,000 to get in the meters cubed, or multiply by 10 to the minus 3, that's the same thing. And then I can divide by the area, so I can do pi r squared, so pi times 8 millimeters, and make sure correct convert, or I can do pi over 4 times the 16 by 10 to the minus 3 meters, all to be squared. And that should give you about 1 meter per second. 0.99, to be a more exact. So it should come very close to 1. Now you can do the same calculation at for 0.2, but since there's a nice sort of conversion factor between 16 and 4, you could save yourself some time in knowing that if the area, so in a sense the diameter decreases by a factor of 4, that means that the area will decrease by a factor of 16, meaning that the speed at 0.2 has to be 16 times larger than that at 0.1. Hopefully that's not too fast. So again, it's just doing a proportional reasoning that I know that V1 A1 equals V2 times A2, but I know that A2 is equal to A1 divided by 16. So then that makes that V2 is 16 times V1, which is about 16 meters per second, or some additional rounding, it's 15.9, but we'll go to 16 meters per second. And that's, these numbers are just working out, I don't want to get maybe confusing with the 16 and 4, this is working out because the speed ends up here being 1 meter per second. So then 16 times 1 is 16, it just so happens to be the same numbers for diameter, but this is a speed and that's a diameter, completely different units, so I don't want you to make any connections there. Okay, so that's a bit of work that we have to do to figure out these two speeds, and then think about, now we can return to the differences in the pressure. So P1 minus P2 is going to be 1/2 of 1,000 kgs per meter cubed. Final speed is 16 meters per second, all to be squared, minus 1 meter per second. If I round up a little, all to be squared, it's going to end up being around 1. And I believe that this gives you the differences in the pressure is 1.26 by 10 to the 5 pascals. So that means that the pressure at point 1, which we should predict, is higher. It's higher by an amount of 1.26 by 10 to the 5 pascals. It's a pretty significant difference. That should cover all the key parts. Again, ideal fluid flow question, think about Bernoulli's equation, think about whether it's a change in diameter or change in height. In this case it was just a change in diameter, no change in height, so we're just looking at the change in the 1/2 O V squared terms. I gotta think about continuity to figure out the actual speeds. I can shorten my calculation time if there's a simple ratio, simple division of the diameter change. I can then think about how the cross-section area changes, to think about what happens to speed, and then finish the question. So choice